Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and this is the conclusion of our lecture entitled Derivatives of Inverse Trig Functions and Such. When last I left you, you were working on this problem, and I hope you finished it, but just in case you didn't, you know what to do. Let's see how you did. Well, here you see it is a chain rule because this is the arc sine of u, where u is 2x. So the derivative is going to be the derivative of the arc sine, which we've now memorized is arc sine of u is going to be 1 over, this is going to be the square root of 1 minus u squared times du dx, which is 2. And we could simplify that by noting that 2x whole squared is 4x squared. Similarly, the derivative here is the arctangent of, we have a u, so we have to use the chain rule. So this is going to be 1 over 1 plus u squared, and u of course is 3x, so it's 3x whole squared times du dx, which is 3. And again, we note that 3x whole squared is 9x squared. This example is going to be a little bit more complex. Here we have the arc sine of u, but u is the square root of x, that is x to the 1/2. So the derivative of the arc sine of u is going to be 1 over the square root of 1 minus u squared. But u squared is the square root of x squared, so that is just x. And then I have to take this times du dx. So this is going to be 1/2 x to the minus 1/2. And then I simplify this by changing the negative exponent into a radical, and now I can distribute it this way. Algebra is your friend, and I will probably ask you to plug in numbers, and so you can go either way here. Last example in this suite, we're taking the derivative with respect to x of the arcsecant of 2x. So u is e to the 2x. So the derivative here is going to be 1 over the absolute value of u times the square root of u squared minus 1 times du dx. But the derivative of e to the 2x is going to be e to the 2x times 2. A lot of chain rule going on here. Notice that the e to the 2x is in the top and the bottom, so they will cancel. And the absolute value is not required because e to the 2x is always positive. So this is a fully simplified answer. Here's another problem for you to do, and so you know what to do. Let's see how you did. Well, the derivative of the arc sine is just 1 over the square root of 1 minus x squared. Now this is the product rule, so it's going to be the first times the derivative of the second. Now this is 1 minus x squared whole to the 1/2, so it is 1/2 times 1 minus x squared whole to the minus 1/2 times the derivative of what's inside, which is minus 2x. Now that was the first times the derivative of the second. I have to finish this product, and then it's going to be the derivative first, which is 1 times the second. So this is what we have as a step before we do simplification. But as advertised, this can be simplified, because if you do the simplification, you will see that this is 1 over the square root of 1 minus x squared minus x squared over the square root of 1 minus x squared. That means that this has a common denominator, so this is 1 minus x squared over the square root of 1 minus x squared, which simplifies to the square root of 1 minus x squared. We're adding that together here, so we're adding one thing to exactly the same thing, so we have 2 of those. So that is the simplification for that problem. Now, we do have some theorems we should make note of. Recall that the inverse of a function really is just the reflection of the function about the 45-degree line. So if you have a function that is continuous, then clearly the inverse is going to be continuous. If you think about it for a while, if f is increasing on its domain, then the inverse is also going to be increasing on its domain. Similarly, if f is decreasing, the inverse is decreasing. And if there's a tangent line everywhere at a point for the function, then you clearly could draw a tangent line for everywhere where the derivative is not equal to 0. So you see that there is the situation that if f is differentiable, then in general f inverse is differentiable. Okay, and we know how to compute that derivative because we do exactly what we've done several times. So if f is a function that's differentiable and the inverse of f is g, then g is differentiable and g prime is equal to 1 over f prime times g of x, provided the denominator is not equal to 0. This is exactly what we've done 4 times in this course. The proof of this is not hard. So here's an application doing that. So we say let f equal 1/4 x cubed plus x minus 1. We ask what is the value of f inverse of x when x is equal to 3, and we also ask what is the value of f inverse derivative at x when x is equal to 3. You know what to do. Let's see how you did. Well, first of all, we can discern that f is 1-to-1 because if we were to take the derivative of f, we get f prime of x is equal to 3 over 4x squared plus 1. That means the derivative is always positive because 1 is positive, x squared is positive, so this is always greater than 0. That means the function is always increasing. That means it is 1-to-1. That means it has an inverse. Now, the traditional ways of finding the inverse would be very difficult in this because you would end up having to solve a cubic. That's not an easy thing to do in general. But what we can do is we know another thing, just to answer part A, we know that if the point 2, 3 is on the function, then 3, 2 is on the inverse. So you see, because f of x is equal to 3 when x is 2, we know that 3, 2 is on the inverse. So that means if we plug in 3, we will get 2. You want to think about that for a while, but that builds on your pre-calculus knowledge. And we just had a theorem that says because f is differentiable and has an inverse, the theorem we just talked about said the derivative of the inverse at the point 3 is 1 over the derivative of f at 2. Notice that the 2 and the 3 are different values. But you see here, we do know what the derivative of the inverse is because the derivative of the function is, because the derivative we already calculated that was this, so we know the derivative of the inverse function at 3 is 1 over the derivative of the function evaluated at 2. I plug in the value and I get 1/4. This is a useful example for you to study, so take some time with this. Here you're supposed to show that these graphs f of x equal x squared and f inverse of x equal the square root of x are the slopes of the graphs are reciprocals. We're going to be applying this same theorem to this pair of points. If 2, 4 is on the function, then 4, 2 is on the inverse. If 3, 9 is on the function, then 9, 3 is on the inverse. So we're applying that theorem again. You know what to do. Let's see how you did. So what you should do is at 2, 4, the slope of the graph is f prime at 2 is equal to 2x. You substitute 2, you get 4. Now at 4, 2, the slope of the inverse is f inverse prime at 4 is equal to 1 over, and here's what f inverse prime is, 2 times the square root of 4, and that's going to end up being 1/4. So you see these slopes, 1/4 and 4 are reciprocals of each other. Similarly, when you do the other point, you're going to get 6 and 1/6. And here's a picture talking about that a little bit. You want to note that the derivative doesn't exist at 0 because this one function, the derivative does not exist at 0. Now, just to sort of wrap things up, we have a whole bunch of derivative rules now that you understand. Here they're stated in terms of the chain rule because we know about the chain rule, and there's even more than this for you to be committing to memory for future exams because what will happen is we've covered other things like logarithmic differentiation and associated things. So plenty of things to memorize. So hold on tight. In closing, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.